Okay, so in this video clip, we're going to take a look at the diamond dataset that's available in ggplot2, and we're going to more generally use the Tidyverse suite. As ever, when we're using Tidyverse, I'm going to make reference here to R for data science. And then the code that I'm using, the R code, is going to come mainly from chapter 3 on data visualization that demonstrates how to set up and run ggplot2. And then the section here where I think we see the first reference to the diamond dataset here is section 3.7. And the diamond dataset comes in ggplot2 and contains information about approximately 54,000 diamonds, including price, carat, color, clarity, and cut. And there's a few more columns there as well we'll take a look at in a moment. But the syntax that I'm using mainly in this Google Colab is coming initially from R for data science. If we examine to run R in a Google Colab, which is normally a Python notebook, we have to activate the magic R command. Once we do so and have connected to the server, then we can bring in our data and run our code using, first of all, we have to prefix the double percentage sign R and then run R. So for instance, to load in the library here with Tidyverse, get ggplot2, dplyr, forcat, stringer, so on, then library Tidyverse. To understand a little bit what's involved with the data set, we have here the prices. They're for, I think they're 2008 prices. I don't think they're retail prices. I believe they are wholesale prices. It's in US dollars. The range minimum value goes from 326 up to 18,000. And we're looking at the carat, which is typically the size. So each carat is about 200 milligrams in weight. The cut quality is nothing to do with the shape. It's about how the light refracts through the diamond. And again, that's a highly sought after feature. And if to understand a little bit what they mean by the luminosity, the more the light refracts through the diamond, the more the sparkle or luminosity or flash. And if the diamond's too shallow, for instance, some of the light will leak out and the light is not as concentrated. So typically a very desirable feature in a diamond is its sparkle, and that then depends on cut. And we have different categorizations then in terms of cut, ranging from fair, good, very good, premium, and ideal. And then we have the color of the diamond, which is basically if we make reference here to stat duke edu, right? And if you come down, there's a nice schema here identifying D to J, where D here denotes a diamond that has no color, is colorless, and then going up to J is near colorless, and then of course we have KLM, there's some faint yellow, and so on. The most highly prized diamonds seem to be here, D, and in this data set, we'll only consider diamonds ranging from D to J. D generally denotes a higher valued diamond, although it's possible there's some diamonds that have very particular colors, yellow and so on, and they are also very highly prized and command high market valuations. Okay, so there's some exceptions here, but we're only considering the range from D to J in this particular data set. And then also important in terms of the diamond, we have a category here for clarity. And clarity is basically, you can kind of see a flawless diamond, if you like, has none of these imperfections. And then as you go through, you see a little hint of maybe a chip or some imperfection in the diamond. And again, clarity is something that's important, but it's not, it would appear to be in entirely linear type situation. And we have some reference here to the clarity of the diamond, the range. This is the GIA. So I'm looking here at Wikipedia, diamond clarity. And the range we go from is FL, which is flawless, then IF, all the way through to I3. Now, I think in the range we have in the Tidyverse dataset, we're going from IF to SI2. And looking at what we have here, we'll see in a moment, but there are some useful links here. Understanding the clarity of the diamond, you can follow those. And in terms of the clarity of the diamond that that will command the highest valuations are those diamonds that are internally flawless. Again, it's not entirely nonlinear, and so we have to take account of how these different the four C's interact with each other. Okay, so also there's some reference here to X, Y, and Z referred to, and if we to understand those values, the X here seems to be the girth of the diamond, and then the table width. This is the table. This is the pavilion of the diamond. The Z depth is from the girth down. The Z is going from the crown down to the base, so the base of the pavilion, and then the depth can be estimated as taking the Z depth divided by Z multiplied by 100, and the table is equal to the table width divided by X, so the girth, and then multiplied by 100. Okay, so okay, I've left these other links here, and I encourage you to take a look. I think they're informative. Again, diamonds, this is an area you just can't learn in 5 minutes. It takes years of skill and experience to understand the nuances. For our purposes, we purely want to demonstrate how we can understand a little bit the data through visualization, right? So we want to do some of our storytelling here in our Tidyverse, and we're going to take a look at how ggplot2 works in R, and how the ggplot2, which is a very popular visualization tool, can be set up in Python as well, and look at how we can work through. Now, we've loaded in our Tidyverse into our environment. We're taking a look at what's in the database. So again, it's 53,940 diamonds, and we've 10 columns of data: carat, color, cut, color, clarity, depth, table price, X, Y, and Z. I encourage you to take a look at those links. They're quite useful. And the medium one here also, in terms of setting up a regression approach to predict the price of diamonds. That's very interesting. And we'll look at that at a later date. To get some overall descriptive statistics, then using summary, we can see that the minimum carat here was 0.2, the maximum was 5. So 5 carat diamond seems to be quite a big diamond. The different frequencies associated with the cut. So there's fair, good, very good, premium, and ideal. And these are organized in a non-alphabetic way. And I think we're going from the lowest to the best, right? Then in terms of color, we're going from D to J, and G here seems to be the most popular category for color. And then for clarity, the IF is the, now we have other here, so there's, it's not giving us all the categories, but we can see the breakdown, right? So IF must be rare enough. Let's look at the depth. We have minimum 43, median 61, mean 61, maximum 79. Okay, and the price may be the most revealing in terms of the how we would understand the value of the diamond. Obviously, price summarizes a lot of the attributes and reveals how in the marketplace these diamonds are understood to command the value. The lowest price is 326, the highest value is 18,000. Okay, so let's take a look at cut here for a moment, and we get a breakdown in terms of the frequency, the distribution of each. I think we could do maybe something similar for clarity, but quite a few that are, the bulk of the diamonds are in these categories here. And then the fair and the good, that they're less common, right? So the cut generally is considered way more diamonds have an ideal cut and premium cut compared to fair and good. Okay, so that's quite revealing. What about the clarity of the diamonds? Let's get some kind of sense. Now remember, IF is the most sought after, right? It's the flawlessly, internally flawless diamonds. And that's the highest categorization here. And as we go through, you can see I1, not so common, but these ones are very common, right? And then there are obviously some more here compared to here. So internally flawless diamonds, these are actually quite rare, right? When we look at the breakdown. Okay, okay, so that's useful. Now we talked about the cut, carat, and the clarity, right? And the color. So that information is conveyed there. Let's look at then, take the cut again and set that up as a bar chart. And we could take clarity and do something similar, just to give us a feel of the overall distribution of the data. And again, IF seems to be quite rare. This is the highest ranked diamond here. And then we have the S12 and S11 and so on. Okay, so again, could be important in terms of valuation, and we would like to take a look at that. Put that, change that back to cut and run the ggplot syntax where I'm saying, look, this is the data and I want to create a bar chart, and on the x-axis we're using cut. Okay, this is the breakdown in terms of the bar chart. Now, important perhaps, we'd like to write out the diamonds dataset as a CSV file. That would default to the content folder, so that would run in. So we've originally taken the data in through the ggplot2, but here we have that data set. If I double click, it'll open as CSV. It's too big to view here, so you can download, and it might take a moment. We can open the file just to see what's in there, and what we see is the full range of diamonds. There should be 53,400, it's 53,940. Right, and we're getting a kind of, maybe just eyeball the data a little bit. Ideal, the cut, the carat, right, the color, the clarity, table, the price. So a lot of these diamonds here, it looks like they're 2,000, lots of diamonds in the 2,000 range. Let's run down a little bit more. 698. Okay, so lots of diamonds on those lower price schedules. not many touching 18,000, 15,000. It would appear if we just eyeball our data. Okay, so but we'll look at that a little bit more in a moment. Right, let's get back into our Google Colab project. Okay, so we could set up a tribble. And again, this is the same frequency distribution as what we would have seen in our, and so this is not in any respect different from the frequency of the diamonds, in terms of the cut, the fair, good, very good, premium, and ideal. The numbers we've introduced here is the same as the actual diamonds tidyverse data set. And we can run again the data, but relate it back to demo, and then do a bar chart. And then on the x-axis, it'll read cut. On the y-axis, it'll read frequency. And then the stat identity is provided fair, good, very good, premium. Okay. Then we can get some basic statistics. And for instance, take the price here and the standard deviation of the price and the median price. So the typical price is 2,400 and the mean is 3,900. So it looks like we have a frequency distribution that's skewed, where we have a mean value that's higher than the median, right? Which means that we have a number of outliers skewed towards those higher prices, right? We can break it down by cut. So again, we're using here, taking the diamond data set, we're using the pipe operator, and then we're saying group by cut, and then summarize and do the counts. Now, another way of, obviously, we could put in could write in clarity and execute again, and we get that breakdown. Now, we've seen that before, but this is a nice way of revealing how to set out using the plier syntax, the frequency of each of the different categories. Could look at, again, back to cut. Okay, and then here we'll do the same, but we're getting the percentage, and only a small amount of diamonds are fair or good, and the bulk of diamonds are in these three categories. So in terms of cut, most diamonds have a good cut, and then we can use ggplot2 syntax to create a scatter graph, and this is for the entire 53,940 diamonds in our data set. What we have is we can observe, look, as the carat size increases, the value of the diamonds goes up, right? So obviously, if it goes up like this, it would tend to indicate that the diamonds are more valuable, but it's fairly clear as the diamond becomes bigger, it becomes more valuable, right? That would be a fair summary here of what's going on. Now, what we don't have, and what ggplot is very good at doing, is breaking apart in the graph different categories. And so look at how this price behavior works for a particular cut or particular clarity, right? So if we change the syntax here in the ggplot without making enormous changes to the verbs and the syntax, we can produce graphs that reveal a lot more. But it's very evident that the tendency is the relationship between carat size and price is a positive one. There seems to be some nuance here, of course. And of course, we've a pattern of, there seems to be an overrepresentation of valuation, right? When we look at where most diamonds seem to just get over the 2 carat, just get over the 1 carat, if we look at the categorizations, and this probably is that when you're very close to a particular carat size, it's moved over, because I would expect otherwise an even distribution of those dots. So why exactly at carat 2, carat 1, we get this sudden increase over representation, and then going up to 2, it gets less frequent, and then we jump and we've over representation. So I think this is something to do with the GIA classification that we are putting diamonds. Maybe this is like car plate, registration plate type phenomenon, that we get a lot of car purchases just over a certain level, but there's an over-representation. So that's a pattern there in that data, but it's also very simply, we can say there's a positive relationship between carat and price. In other words, increase the size of the diamond, the value tends to go up. Okay, now when we run the same code, but say fill, right? In other words, take the color, use color here to equal color. Now that means on the x-axis we had carat, on the y-axis we had price, but separate each of the different diamonds based on its color and map it separately with a different color. Remember, color denotes if we can take a look here, the color of the diamond goes from D to J, and D is the most valuable, J less valuable, all else being equal. Okay, so when we run the same command again, and it's identical to the one before, and we're creating a jump point graph, which is a scatter graph, you can see, yes, D, there's a higher concentration of D. Those are the diamonds where they're almost colorless. And there's, when we look at J, more of a clustering, more evidence of J being further out. In other words, yes, there are J diamonds that command these high valuations, like maybe $17,000, $18,000, but all else being equal, their carat size is bigger. So to reach the higher valuations, the J diamonds tend to have to compensate by being bigger. And we note that D diamonds, their price escalates very quickly as we increase the size of the carat. There are some D diamonds that are here and here and here, which seem to be the exception to the rule, but there must be something else going on, right? Again, we could do the same analysis again and break it apart for clarity, run the same command as we had before. And this is the real value associated with the ggplot2, that we can take a look at our graph and see, is it true that the IF diamonds, the internally flawless diamonds, all else being equal, tend to command a higher valuation at those lower carat sizes? And that would seem to be in evidence here, right? We don't see many. I think there's one here, but we don't see any outliers, right? So clarity seems to be quite important in terms also of the valuation of the diamond, right? And we can go a little bit further down and look at the cut, and we can say, what is the effect of the cut? Now here, it's not the ideal, which is the highest register. There's more of an intermingling of the dots. So cut is very important, and that would be the anecdotage. And when you go into a diamond shop, I think that's typically what is recognized as being a key characteristic. You want a good cut. But when we look here, we see, yes, it's true, the ideal cuts do command higher valuation, but there is more, and there are a number of exceptions here, right? So other factors obviously taking precedence. Now, or this ggplot2 package is an extremely useful package. We're using it in R, but we can also use a ggplot. There are a number of different ggplot analogs in Python. And the one I'm going to explore here, we're going to do pip install with plotnine. So pandas plotnine. And then we'll import in NumPy, pandas, matplotlib, seaborn. There's a palette of colors here we're going to make available in this environment, and matplotlib. And then also very important, plotnine. Now we can read the diamonds from here, our data set, to bring into our pandas or our Python environment. But also just to note that this same diamonds database is now available in Seaborn, or you could read it indirectly from this GitHub, right? So either of those three, any of those three approaches would allow us to bring in the diamond data set. When I execute, take a look at our diamond. So let's read in our CSV file from here. Then take a look at the first 5 rows, and we see here this index, additional index has been included in. So we would like to drop that using this pandas command. We're going to drop this first column here, and then when we take a look again at diamonds head, diamonds dot head, HEAD, then that first column should be removed. Okay, so let's run that. And you can see now that first column is gone. So we're just starting with carat, cut, color, clarity, depth, table, price, XYZ. Okay, and some information then about what's in our data set that could be quite useful. We can print off again using pandas command, print off the different categorizations in terms of cut, in terms of color, in terms of clarity, right? And if we come down here, you can see having imported in plotnine from plotnine import and doing the pip install, we can run the same analysis as we had before. So for cut, here we have carat, and on the x-axis we have price, on the y that was exactly the same as before, and we have color. And then our data set is equal to diamonds, and we're using a scatter graph, right? And again, what we see is the ideal, more of a representation of ideal, then premium, then very good, and then the fair cuts. We can see it takes a much bigger carat size to command higher valuation when the cut is fair. And if we change that to clarity, again, we're using in the Python environment, the ggplot2 syntax, again, which is very attractive here because it allows us to take this very big data set, and we can see here with IF, which is the internally flawless, it's the best. We can see how there's a preponderance of the internally flawless diamonds commanding the higher valuations at those lower carat size, all else being equal, right? So that's very useful, and we can see here this is the lowest register, the I1 in our data set, and again they command lower valuations at the same carat size, all else being equal. So that's fairly clear. So we've done color. Let's go with color here for a second and take a look. And again, keep in mind that D is the best, J is the worst. And again, where the diamonds are colorless, they command the higher valuations, and where there's more of a tint of yellow, all else being equal, we've more a preponderance of those J's. Other factors obviously affecting the valuation, but there is a clear pattern, right? That the diamonds that are colorless have this, command these higher valuations. Okay, and that's clarity again. Okay, so we could take a look at the correlation matrix here, and we could look at price and depth and table. These are numerical values, and there's a strong relationship between price. So I presume it's the bigger Y, X, and Z are, the bigger the diamond becomes, right? And there's a slightly negative relationship with depth. Okay, but these are proportions, of course. Okay, so that's our, and again, maybe one more thing here worth pointing out. We can also use the syntax of facet wrap, right? So if we just remove this for a moment and look at, we can employ in the Python environment ggplot X on the horizontal axis, Y on the vertical axis, and look at color. And then we've different shapes. Now it's difficult to distinguish the shapes, so it's not particularly a very compelling graph because we've just too many shapes, and it's too numerous, right? So it could work if we had a smaller data set, but because we have 53,000 data points, almost 54,000 data points, the shapes are not that revealing. Okay, so that's just as it is. But if we had a smaller data set, interestingly though, we can use the facet wrap syntax that's available in ggplot2, and something similar here, facet wrap and color, right? So facet wrapping is also possible in the ggplot plotnine syntax in Python, and the experience we have in RStudio, we can almost replicate in this Python environment. And again, that demonstrates a little bit the desirability of ggplots, its popularity, and also the extent to which, if a particular package becomes popular in R, it tends to transfer across, and vice versa. Okay, let's stop the recording here.